Okay, I think we should start now. So, hello and welcome to the very first episode of the professional presentation series by Structural Engineering Institute graduate student chapter here at Michigan Technological University. We are very excited today to host our first official event as a newly established chapter here at Michigan. Purpose of this professional presentation series is to expand the knowledge in the field of structural engineering and promote the state-of-art innovations and research with special focus on the needs of the future generation of structural engineers. Today, we are thrilled to have our faculty advisor of our chapter as our guest speaker, Dr. Daniel Dowden. Dr. Dowden is an assistant professor here at Michigan Tech. He received his Ph.D. from University at Buffalo in 2014. Upon graduation from University of Buffalo, he stayed on for 2 years as a testing engineer, conducting service to industry, seismic qualifications, shake table testing at the Structural Engineering and Earthquake Simulation Laboratory at the University of Buffalo. Prior to receiving his PhD, he was practicing structural engineering in Seattle, Washington for 10 years, responsible for the design and project management of new building construction and seismic rehabilitation of existing building projects. Today, he will be talking about the earthquake resistant to seismically resilient, diverging from the disposable buildings. We will be providing the time at the end of the presentation for any questions from the audience. And for those who are joining us online, for our online audience, if you have questions, you can submit your question in the chat box, and we will address your presentation your questions at the end of the presentation. So without further ado, please welcome Dr. Daniel Dowden.
Thank you, Armin. Can everybody hear me? Hopefully everybody can hear me across the internet there. But as Armin said, my name is Dan Dowden. I'm assistant professor here at Michigan Tech. Relatively new faculty. I started in 2017, but a lot of what I'm going to present here is based on my research interest as well as my professional experience. And if there's any questions in the audience here, feel free to raise your hand. I have no objection to answering questions on the fly. But this presentation is not necessarily meant to be highly technical, because there's a lot of folks in here and possibly who are listening in that aren't necessarily have a background in seismic engineering. So the presentation outline is, I'm going to start out with an introduction. I'll talk a little about the current standard of practice in seismic design and performance objective for standard buildings. Then we'll talk about seismic force resisting systems and what their expectations are. Specifically, I'm going to lump that down into conventional systems. This is what I call disposable buildings, and hopefully that'll make sense more when we get there. And then finally, what I'm considering as the next generation of buildings is low damage, or what we call seismically resilient systems. And finally, I'm going to end the presentation with some related current research works that's in progress that my graduate students are working on at this point. That my microphone keeps on falling. Okay. Earthquakes. I think it's pretty well understood that earthquakes can be very devastating. These are images that obviously aren't the way we're supposed to design our structures. So these are all extreme events. Some viaducts, building collapses, so Loma Prieta, the Chi-Chi. We've got building collapses in Chile earthquake, and the Haiti earthquake. These are all relatively recent events. And there's a most recent 2018 in Taiwan. And what's kind of not worrisome is that these are relatively modern cities that these are happening in, modern structures. And so the question is, what can we do to improve this or actually prevent this? So a little background on seismic design for those of you who aren't necessarily have had the experience or even taken a structural dynamics course. But as an undergraduate, we all take steel design, reinforced concrete design, timber design, all of that stuff, and we're designing for gravity loads, right? But until you get into a graduate level course where you're taking structural dynamics, you get realized that we have to consider lateral forces as well. The main two ones are going to be wind and seismic. So there's a big difference when we design for seismic compared to wind. So wind, we essentially design for elastic level forces, but earthquakes we design for inelastic response for reasons we'll get into. But what I've got is and excuse the chicken scratch, but that's a sketch that I put together of essentially a building frame system with some lateral loads on there. And we have, for the lateral system, some X-bracing, okay? On the right-hand side, if we push that building, say we're doing a pushover analysis, and we push it until we get damage in the building, you're gonna get a force displacement response. So if we're taking a look at the response of the building, at the top, we've got the displacement, and finally at the ground level, what we could call our base shear. So what you see in that force displacement response is that we have an elastic response, and then somewhere along the building we get yielding, and we get this plateau, and then we can unload. And so what you see is we're developing these hysteretic loops. And this is what we want to see when we're designing for earthquakes. The bigger these loops, the more energy dissipation that we're providing. So kind of the approach for earthquake engineering in past decades is we want these huge full loops, because that tells us we're dissipating or maximizing energy dissipation. But if you take a look at the zero displacement, or excuse me, the zero force, so we have an event, right? There's going to be a point where the building will settle, right? And the earthquake will stop shaking, the building will stop vibrating, and then you'll have a point where there's zero force on the building. So if you take a look at that very simple plot, at the zero force location, wherever that hysteretic loop crosses is your residual displacement. So that means you're going to have a building structure that has a residual lean, right? And if you have a residual drift, that means that your building can be susceptible to P delta effects under self-weight. It could be susceptible from cascading seismic events such as aftershocks. So that is that's a cost that we accept when we accept these big energy loops, is that we can potentially get large residual displacements at the ends. So seismic loads. So how do we calculate seismic loads? Well, this is the equation of motion right here. So one way is to solve the equation of motion, and typically you would, obviously it's not practical to do that by hand. You would do that in a program such as OpenSea, SAP 2000, or whatnot that actually will do the numerical integration for you because you're utilizing the integrator in the program. But the problem with, I wouldn't say the problem, but the nonlinear response history analysis that you would conduct in, say, OpenSea, you have to have a numerical model. And numerical models require, if you want to consider what the inelastic response is, degradation models of how you properly model your connections and things like that. And computationally it becomes very expensive. And oftentimes, at least when I was in practice, it was very seldom done, at least depending on what you're designing, but more often than not, you're looking for more of a, I guess, an easier solution or approach. And that brings us to the equivalent lateral force procedure. So this is taken directly from the ASC 710. So what we have in that code is a very simple equation. V is equal to C times W, which W is going to be your seismic weight, and then C is some sort of a seismic coefficient that you determine. And there's an equation 12.8-2 that's shown down below. And essentially, when it comes down to it, this is just F equals mass times acceleration. But what it's doing is, this ELF procedure is a static, elastic analysis approach, and it allows engineers to calculate these by hand. So you can calculate these calculations readily by hand, and then you can put it on your structure, you can do the statics, and you can come up with sizes. Now, the reason why I brought this up is because if you look at the seismic response coefficient C sub S, there's a value S sub dc, which is our spectral acceleration, divided by R divided by I. Okay, so I is what we call the importance factor. That's typically 1 for typical buildings. So essentially what you're doing is you're taking the spectral acceleration, which represents the maximum acceleration response that you're going to get on your building, depending on what your site soil conditions are. But you take that and you divide it by this factor R. So the R is the response modification factor. Okay, whoops. So if I go back to a force displacement, I'm sorry? So if I go back to a force displacement response, remember that hysteretic loop I was talking about, and that was basically going through a cyclic response. But if I'm just doing a pushover, I take my building and I push over until it collapses, this is what I would see. So I've got a curve on there at zero displacement, zero force, and I'm pushing on my building and I'm getting this response curve. And if I design my building to remain perfectly elastic, this means I'm using an R of 1. I would continue on that elastic trajectory line that's dashed, okay? This represents the actual response of our building, the actual forces that we would see on our building. But for design, we take what the expected seismic force on our buildings are, and we divide it by this factor R, okay? And then you can see that once you take that spectral acceleration divided by R, we're designing our building in an area that it's going to be damaged. It's going to yield, okay? And then there's these other components. There's this delta sub X and this omega factor. So these are all factors, multipliers that we use to multiply our response, which are elastic response, to basically get the response in the inelastic range. For example, if I'm trying to figure out what my building displacement is for a design event using the ELF procedure, well, I have to multiply by the C sub D factors, amplification factor, which could be on the order of 2 or 3, and that represents what my actual displacement is going to be based on damage. So the issue is, what do we use for R, and how confident are we in our building to use this value of R? Okay, and this R value is all based on predicting the performance of our seismic force resisting system under an earthquake, factors on how ductile our building is going to be. If we have a ductile system, meaning that it can yield a lot before fracturing, then we can typically use a larger R. In essence, it comes down to reliability. And we can calculate this R factor. We use the FEMA P695, which is a probabilistic framework, and it's specifically designed to quantify these building seismic performance factors, okay? That being said, we know for earthquakes, our building is going to sustain heavy damage, and this is the design level earthquake. This is an earthquake that's going to, the return period is 500 years to 2,500 years. So we know that it's going to be damaged. So I like to use the crumple zone analogy for those people who don't really understand how we design buildings for earthquakes, at least in modern code. So if we have a car and we have, and I'm showing the car as a pre-earthquake, and then we have an earthquake that happens, that means your car has gotten into an accident. And you can see that in the front of the car, there's this crumple zone, okay? So these crumple zones are designed, they're built into the car. The reason being for life safety. So after the car accident, you can safely step out of that car and walk away. So this crumple zone is exactly what we do for buildings, for earthquake engineering. We provide these crumple zones that dissipates the energy safely and predictably so that you can walk out of a building. Now, after the event, the building is about to collapse. In terms of the code, engineers, you can say, well, that's fine. We did our job. Life safety, collapse prevention, you can get out of the building. I really don't care beyond that, what happens to the building. Okay, so building systems, conventional seismic force resisting systems, the crumple zones that we have, looks like this. So I'm just going to name a few of the seismic force resisting systems that we use. And this is what we call a SMRF, or a special moment resisting frame. So here we have a column. So on the left-hand side is a SMRF connection, obviously before damage. But essentially what it is, it's a column and a beam with a rigid connection. If you take a look closely at that beam, you can see that the top and bottom flanges are coped, and that's a reduced beam section. So we're actually detailing into our beams a weak zone. So the idea is that when this frame, which is designed specifically as a special steel moment frame, it's going to develop a plastic hinge at that location. Okay, and the plastic hinge, when it forms, is what you see on the right. And you can see that the top, the bottom flanges will buckle, you'll get some yielding in the web, and so forth. But this is the expected behavior of a SMRF, okay? This is what we want to happen. Now, if we look at a steel concentrically braced frame, so those are some configurations of brace frame. So here, unlike the moment frame where we're dissipating all the energies in the beam and column connections, we're providing all the energy dissipation in the brace elements. And so you can see on the bottom some pictures from testing of what the expected failure or the expected energy dissipation is. And so on the far left-hand side is a brace that's gone through many inelastic excursions and has severely buckled. And then on the right-hand side, you can also see that the gusset plates are tied to the beam, and you get some yielding and plastic hinging that occurs in the beams. And keep in mind that these beams are also the beams that support gravity loads. So these are coupled with your gravity load system. Another type of lateral seismic force resisting system is what we call an EBF, or an eccentrically steel braced frame. So it is kind of like a braced frame, but what it has is, this is an inverted, what I'm showing here is an inverted, well actually the author here, what they're showing here is an inverted EBF. So what the key thing to see about this type of system is there's a link. And this particular author is proposing a replaceable link, which is getting closer to the seismic resiliency that we'll talk about later. But take a look at his tests. in the lower right-hand corner. So essentially the EBF dissipates all the energy in this link beam element, okay? But look at the distortion that happens, the amount of yielding that occurs. And this is an idealized test setup. Just remember that this beam is also part of the floor system. It's actually supporting the slab on metal deck, okay? So how do you repair this? It's one thing to test it, but how do you repair it? Even though this author is saying, hey, we're putting these splice locations here that we can, during an event, we can pull it out and we can replace it. But just think of this. How are you going to pull that link out if it actually supports your floor, right? You're going to still have to go in and you're going to have to shore up the flooring to support the floor that this beam supports in order to take this link element out. But it's getting closer to more seismic resilient systems, okay? Okay, excuse me. Now I'm getting into my field of interest and research is seismic resilience. So what we just covered are the conventional systems. Those are the expectations that how we currently design our buildings. Now if we go back to our car, and using the crumple zone analogy, we have our pre-earthquake condition, right? We have the earthquake event, but after the event, what if we can go back to this, I'm going to call it the pristine condition. That is the motivation for seismically resilient buildings and bridges for that matter. So resilience, so I have a definition of resilience, and I've taken it from Dr. McAllister, from one of her papers. I'm just going to read it, and it says the resilience, the ability to prepare and plan for, absorb, recover from, and more successfully adapt to adverse effects, okay? So we're just taking this concept and making our buildings seismically resilient. And, you know, you might think, well, okay, what is the significance of seismic resilience, okay? Well, the real motivation is in highly urbanized areas. So remember I started out this presentation and you saw the photos of the devastation that can occur in highly urbanized areas, right? So if we can have an infrastructure system and buildings that basically can recenter themselves and can be easily repaired, that's a big deal, okay? So before I really get into things, the whole concept of seismic resiliency is not new. So the Greeks had it figured out. So this is the Parthenon. And if you take a closer look at one of the pillars, they're segmental. They're segmentally built, and actually what's not shown here is they actually have, at the base, it allows for rocking, and they actually had some energy dissipating elements down there. So they had rocking systems. So when it comes down to it, seismically resilient systems, we're emulating this. We're emulating the rocking, okay? Now in the United States, the whole idea of seismically resilient systems really, the big catalyst was in the early 90s. And that was with the PRESS program, which stands for the Precast Seismic Structural System by Professor Priestley, okay? And so the real motivation behind this test was not originally for seismically resilient buildings, but it was an NSF project with PCI, Precast Concrete Institute, and they were looking for ways that they could build these precast structures very quickly. So they thought, well, let's eliminate connections and we'll just tie all the beams and columns together with post-tensioning without any connections. So that's what they did. They tested it and they realized, hey, these things recenter. There's not a whole lot of damage, okay? So it really started with the PRESS program. And then from the PRESS program, they realized, okay, yes, these systems rock, And specifically, there's one of the connections. They got the column and then they got the beams. There's no connection, and they just ran high-strength stranded post-tensioning unbonded strands through the middle, okay, for a clamping force. Okay, and they ran tests and they found that as joints opened up, things were recentering, but it did not provide a lot of energy dissipation, okay, because the building system remained essentially elastic. If you have an elastic system, you're not dissipating any energy. Okay? So then Professor Stanton at the University of Washington, who was a part of this program, said, hey, let's make a hybrid connection. And they started putting in bonded reinforcement, top and bottom, energy dissipation. So the hybrid connection, along with this rocket connection, really was the catalyst in seismically resilient walking systems. And you can see right here, as I'm showing, the self-centering response. So the self-centering response on a hysteretic response, force displacement, is flag-shaped. So just remember a flag, okay? So the press, after the press test, researchers started saying, hey, let's implement these connections into steel moment frames. So instead of having a steel moment frame that was rigidly connection, they said, hey, let's put a rocking connection in there, and we'll put in some energy dissipators. So this is very, if you look at that, that's the hybrid connection that Professor Stanton developed. So that being said, this is a steel moment frame with a post-tensioned beam column rocking joint. And if you take a look at the hysteretic response, we have the PT boundary frame, okay? We have the component provided by the energy dissipators, or what I call the structural fuses, and then the combined response below, which is your characteristic flag shape for a self-centering system. Now, a couple of things to highlight is that the PT boundary frame is designed to remain elastic. Okay? So you want to ensure that the PT doesn't yield and that your beam column, your PT boundary frame remains essentially elastic. And so what happens is you look at the PT boundary frame, I guess figure A, it remains elastic, and as you can see, no energy dissipation. Now, the interesting thing about these PT, I'm going to call it PT, actually Professor Christopoulos calls it a PTED frame. Because PTED frame is that there's a, typically what will happen is they'll put the post-tensioning in, they'll pre-tension it to say 20, 30% of the yield strength or more, and it provides a clamping force, okay? When you subject the frame to a lateral force, the beam and column are not going to rock until that clamping force has become reached, okay? And that is point A on this figure A. So until then, until the joint opens, the frame thinks it's a rigid frame. It thinks it's a Smurf. So what happens is once the beam to column joint opens, and then the stiffness of the frame softens, and you get this bilinear branch, okay? So anyways, but the energy dissipation of the structural fuses does not occur until the gap opening occurs, okay? And then this was also implemented on, again, there's a lot been done with steel moment frames. And here, instead of using these yielding structural fuses, these researchers, they used, instead of these ED bars, they used these angles, top and bottom, as their structural fuses. And there's the hysteretic flag-shaped response. And so the idea is and I guess I should have clarified a little bit more, but the post-tensioning provides a self-centering response, okay? And the I guess let me go back one slide. So the post-tensioning provides the recentering response since it's designed to remain perfectly elastic. So as the gap opens, if something's elastic, it wants to rebound to where it was originally. And so the PT boundary frame provides the recentering, and then of course the energy dissipation comes from the structural fuses, which is designed to be replaceable. So here, the structural fuses, this is a very similar frame, but they're using angles. Again, very similar concept, but instead of using yielding elements, these researchers decided to use friction elements, okay? But the response is very similar, so it changes your energy dissipation shape, but the flag shape response is the same. Then, you know, folks went back to the precast concrete. So same thing, PT provided for recentering, and these energy dissipators, replaceable energy dissipators provided at the beam to column joints. So we talked about steel, concrete, even folks in timber decided to adopt this technology. And so this is a beam to column heavy timber. It's an LVL, and it's a rocking joint again. And you can see that they have these structural yielding elements, and they're threaded through the columns and the beams. And those are the energy dissipators, and again, they've got the unbonded post-tensioning to provide the recentering. So there's a common theme here. Everything's rocking, all going back to the Greeks. Then there's some other variations. Folks decided to say, hey, what if we put in self-centering braces? So this researcher came up with an inventive idea to provide, there's post-tensioning, it's a telescoping brace that has PT plus energy dissipators in it. And more recently, there's been a lot of movement in cross-laminated timber, okay, or CLT. And a lot of this motivation has come through, there's been a lot of mindfulness in sustainable practices. How do we make our buildings not only resilient, but also sustainable? And of course, one of the more sustainable materials out there is wood. They're highly sustainable, sequesters CO2, leaves a low carbon footprint. But so anyways, CLT actually has been a technology that's been around for about 30 years in Europe. It hasn't been until the early 2000s where CLT has been used as seismic walls, mainly for the reason that in Europe that they don't have a lot of seismic active, well they do, you know, parts in Italy and places like that, but where CLT was being used was in low seismic areas where wind was driven. But so this particular wall is, there's a lot of research out of New Zealand that has done a lot in CLT rocking walls and energy dissipators. But so they've got this researcher is using structural fuses based on friction at the base of the wall. So as this wall rocks, as you push on it, as it cycles back and forth, you can see the flag-shaped loops being provided due to that response. And of course, there's some more with using yielding structural fuses. And so that's kind of an overview of research done by others. So during my PhD studies at University of Buffalo, I developed, along with researchers at University of Washington, self-centering steel plate shear walls. And so what is a self-centering steel plate shear wall? First, I think it's best to define what a conventional steel plate shear wall is, because this is a system that's already in the code that is accessible to designers. So all a conventional steel plate shear wall is just a special moment frame with an infill steel web plate. And so it's essentially a dual system, and it provides a substantial amount of energy dissipation through the web plate and also through the Smurf connections. So all we did was, again, going back to the rocking connection, we eliminated the rigid welded connection and replaced it with a beam to column post-tensioned rocking connection. So all the energy dissipation is provided by the infill weld plate, the PT boundary frame, and which includes the PT elements, all designed to remain elastic. And so this little picture here gives you a better idea of the self-centering mechanism. Essentially, when the beam to column rocks, you get a gap opening. That gap opening elastically elongates the post-tensioning, and that elastic elongation, the PT just wants to recenter. It wants to go back to where it was, as that provides a self-centered mechanism. So energy dissipation on a steel plate shear wall, essentially the infill weld plate is allowed to buckle and shear, and we develop the tension field action. So if you take a look at the picture on the left, we're essentially developing the hysteretic energy through pure tension. And one of the big assumptions that have been made in steel plate shear wall systems is that it's a tension-only behavior, okay? And so if you look at the response down below, I've got the PT boundary frame, which is bilinear elastic, and then I've got the infill web plate. So tension only simply means that if you look on there, I've got two quadrants on the force displacement curve, 1 and 2. So once I go through an inelastic excursion of 1, when the frame unloads, it unloads at A, and then you get a reverse cycle if you're doing a cyclic test. And then if you push it back into the positive excursion, you're not going to dissipate energy until you regain that point A. So once you get to point A, you get divergent material, you dissipate further energy. So that's what we call tension-only behavior, and that's the assumed behavior of these SPSWs, which is ideal for self-centering systems. So the rocking connections that we looked at. So we looked at 3 different types of rocking connections. So the first one up top is the flange rocking, and this is the system that all the other rocking connections that we looked at were this flange rocking system. That they rock about the top and bottom flanges. So you can see in that cartoon picture there, I've got the rocking points for, in this case, a rightward drift location. But the problem or the issue with this is that I'm showing a gap opening called delta. That is what we call beam growth. So what happens is, in order for that gap opening to occur, the beam literally has to push out on the columns. It literally has to push out on the columns. And hence beam growth, right? And so the issue is when you have a diaphragm on top of that, a real building system. So if you have a real diaphragm on there, rigid diaphragm, how is that going to affect the beam growth? You're either going to cause damage in your diaphragm, or the diaphragm is going to prevent your beam to column gap to open. So that was the motivation for looking at these rocking connections down below. I've got a centerline rocking connection, and the bottom one, which we call a top rocking connection. That was a original contribution by myself and my advisor, Bruno. And so the idea with the centerline rocking is that you don't get the beam growth. You're not going to get the beam growth, but you do get some gap openings, so you get potentially some tearing still. But the news breaks frame, in theory, you get no tearing, you get no restraint effects from the diaphragm because you're always in contact with the diaphragm. That's the motivation. So these are the connections that we looked at, that we had our test frames, the flange rocking, the center line, and the news breaks. And these are our test specimens. And we looked at a full, these are third scale tests, third scale frames. So we had solid infill well plate, and then we also looked at strips. Okay, and this is what the frames looked like. And for these connections at the columns, we used an idealized pin connection. And the idea was that if you had a standard conventional bolt connection, you could generate a plastic hinge there. Being that this is a seismically resilient system, we wanted to ensure that we did not develop a plastic hinge there, so we had a pin connection. So here's one of the static tests that we did. And keeping in mind, the boundary frame is designed to remain elastic, right? All the energy dissipation comes through the web plate. And so as we cycle through these, you can see the damage that accumulates, okay? And no damage occurs to our frame. And then you can think of those mass plates, that's our rigid diaphragm. So you can see all the damage that's occurring. And then finally, it gets to the point where the web plate actually literally tears away from the boundary frame. Okay. So the point being is that after the event, the building recenters, and we can come in and replace those infill web plates without affecting the gravity system. So relatively easy, we can replace those web plates. So here's some of the results. This is the test with the strips. If you look at the force displacement response, perfect recentering. Perfect, you know, kind of flag shaped. And here's what it looks like. Now, when we look at the test with the full infill web plate, the loops are pretty full. But one of the things you can notice that we do have a residual drift, so to speak, is that at zero force, we have a residual drift, and it actually by quite a bit. So this came about for the reason that, remember, we had assumed that the infill web plates were tension only. Well, solid infill web plates are not tension only. They do have some compression strength. And that compression strength is what prevented the recentering, the full recentering of this frame. And at the start of this design, this research project, I did not account for that, but you can design for that by adjusting your post-tensioning, okay? But it turns out it's not that big of an issue for recentering, as we found out when we went to some shake table tests. But here's some plates, the damage before and after the test. Okay, so we also conducted shake table tests. At University of Buffalo, I was very fortunate enough that we have ability to do shake table testing there. And so we took those exact same frames, put them on the shake table. And we used a synthetic ground motion. There's our response design spectrum. And then the loading protocol essentially was that we did a scaled amplitude test. So we had our ground motion. We incrementally amplitude scaled the ground motion because we didn't know how the frames were going to behave. So we started out with low level shaking up till very high level shaking. And then we did white noise tests in between to do identification tests to track the dynamic properties, see how they changed. But this is just a sample loading protocol. But here's the system on the shake table. And okay, and here's a test. It's actually not as, it's more exciting when you're there in person, but so that was an example of a test. But here, remember the whole bit about we saw on the infill web plate that it didn't recenter on our cyclic test? But we put it on the shake table, and recentering for self-centering systems, typically 0.2% residual drift is what is considered recentering. If it's below 0.2%, then it's recentered. 0.2% is simply it's the acceptable allowable tolerance for new building construction. So you can look at each increment of earthquake test that we did, the system recentered just fine. So for dynamic tests, the compression effects that we saw on the static test was not an issue for earthquake loading. And so here's the response due to the with infill web plates. And again, recentering occurred at all of our tests. Okay, I did some tests, full-scale testing in Taiwan of that news breaks frame. That's me standing by our specimen. We did pseudodynamic testing, which basically is a static test that emulates a dynamic test. But we ran it through 3 different ground motions, as shown. And this particular connection, remember the UB test, we used a pinned connection to prevent plastic hinging at the base of the columns. Here we decided to use a rocking connection, which is an alternative. And then you can see here this is the base of our column. And so this is what it looks like on one of the columns of our frame that it rocks. So anything that rocks, that's a natural self-centering mechanism. Okay. And the post-tensioning ensures that we recenter. Okay. So this is the response due to the design level earthquake, and you can see that everything, the residual roof drift is within 0.2%, yielded just fine. Okay, so I want to just quickly talk about some of the current work that I'm doing now with my graduate students. We're working on, so I showed some images of some cross-laminated timber rocking walls. We're developing a friction damper for CLT rocking walls. It's shown here as a schematic. Essentially, on the right-hand side is an idealized free body diagram. So what happens is that as the CLT wall rocks, we've got these 2 wedges. The wedges are connected through the wall through high-strength bolts, which have disc spring washers on them. And so as one block or wedge moves relative to the other, it decompresses these disc springs, and and by decompressing these disc springs, it provides a clamping force. And then with that clamping force, we provide a abrasive friction interface, and we can dissipate energy. And we're dissipating energy and also providing some self-centering response. This is an abacus model of that damper. And you can see that I've got 3 plots here. The first one up top is the response without the dampers, just the wall with the PT. It's our bilinear elastic response. Down below, we have the response just with the dampers, not with the PT. So you can see that it does provide some recentering. And then combining the 2 provides the enhanced flag shape recentering response. So we're getting ready to do some scaled testing in our lab. The first thing that we're doing is we're trying to identify appropriate friction materials. We know we're going to use stainless steel for one, but the question is, what are we going to use for the other materials? So right now we've tested leaded tin bronze, and you can see that we've got pretty stable loops. Coefficient of friction ranges between 0.2 and 0.4. We're going to be doing a thermally sprayed aluminum, and we should have those results done in December, which will inform us which material to select for our dampers. And here is our sub-assemblage test that we're going to be doing in our lab. We've got our CLT wall. This is the existing reaction frame that we have. We've got the uplift friction dampers shown there, and we should have these tests completed by spring 2020. Also, another project that we're working on is we're taking this news breaks frame. Okay, I've got the news breaks frame with the steel plate infill structural fuses, and then we're also taking that same PT boundary frame, but we're using BRB structural fuses. And so the question is, how is, what is the collapse fragility of these systems? And so we're going to be running IDAs, and from those IDAs, we'll be able to develop collapse fragility curves, and using those collapse fragility curves, using the FEMA P695, we should be able to come up with these preliminary seismic performance factors. So the other item I wanted to point out is redundancy as structural engineers is a good thing, especially in earthquake engineering. Of course, here's a simple span bridge that simple spans, and then you've got beam on the right-hand side, redundancy. If you have redundancy, you pull one element out, you can still support it, right? So one of the things that we're looking at is these seismic resilient systems, they don't have a lot of redundancy because the structural fuses themselves are pretty small compared to conventional systems that have a lot more redundancy. They're more, I'm going to say right now they appear to be more robust, right? But here we're providing little elements, structural fuses, such that we can get a recentering response. So one of the studies that we're looking at is main shock, aftershock sequences. So we designed our buildings with these seismic resilient systems to have these structural fuses that are meant to be replaced afterwards. Well, when is the building going to be replaced? It could be months, a year, who knows? So that being said, the buildings themselves are probably going to be more vulnerable to potential aftershock sequences, which are common. And so we ran a small study, which is part of a larger study. We selected 7 as recorded main shock, aftershock sequences. We scaled the ground motions to an appropriate response spectra. And down below is the response spectra of each scaled ground motion. And we ran nonlinear time history analysis in OpenSeis to see what the response was for these 7 ground motions. And again, our OpenSeis models included both stiffness and strength degradation. So the results are relatively reliable. But we did it for the steel plate shear wall one, peak interstory drift. This is actually, the results are actually uneventful, which is good. We've got 2 plots running just the main shock, and we ran another run with the main shock aftershock sequence. And what this shows is that the main shock aftershock sequence does not provide us a response larger than the main shock. So in other words, the damaged building after the aftershock, the response doesn't exceed the main shock event. With the exception down below on the Christchurch sequence, we actually got some PT yielding, and obviously we had an issue there. So this is the peak interstory drift. This is the residual drift. All the systems recentered, and again, but the Christchurch sequence, that where we got the PT to yielding, we got a large residual drift, okay? Which basically states that as long as the PT boundary frame remains elastic, the results are good. If it yields, then we're in trouble. We did it for this, the FRPTED frame. Results were pretty good, fully recentered. So the last thing I want to leave you with really quickly is we talked about structural resiliency, but what about non-structural? So here, so what I wanted to leave you with that was some ceiling testing that I did at Cecil, but everything that we talked about was building resilience for the structure. So obviously resilience includes not just the structure, but all the non-structural components that go along with it. And that's something that also has to be addressed. The first place to start is to ensure that we have a structure that we can work with, that's seismically resilient. So with that being said, this is SEI. I just wanted to plug the Structures Congress 2020 coming up next spring. I'll be moderating a session specifically on diverging from disposable buildings. So if you want to learn more about this topic from other experts, please come see us. Lastly, I want to say thank you to Armin Tater and Alex Baker, who are my graduate students who put together the preliminary results that I provided. And unfortunately, and that's my presentation. So I think I went a little long, but if you're still here, I'll be happy to ask any question, answer any questions. Yes, Pete. Oh.
I would like to thank Dr. Dowden for the informative presentation on seismic resiliency. So if anyone has a question, you can ask your questions that for the folks online. They can also unmute themselves and ask questions.
If there aren't any questions, that's fine too.
So we have one question. How the flexibility of structure members affect the vibration capability of
How does the flexibility of structural members affect the vibration capacity of the structure? Well, that's kind of an open-ended question, and it's difficult to give a definitive answer. So, are you talking about inelastic flexibility? Are you talking about elastic flexibility? So, I'm gonna assume this is based on on the stiffness of the building. So clearly, let me make sure I get that. Okay, so you got moment frames, you got brace frames, we've got shear walls. The flexibility of those types of systems all vary significantly. So moment frames are going to be the most flexible system, and I'm talking about inelastic flexibility, not elastic, because when you're talking about elastic flexibility, then you're just getting into serviceability, vibration, annoyance problems versus safety, seismic performance. Next is going to be brace frames. It's probably going to be the next stiffest, and then finally with shear walls. And that's all going to affect your accelerations. So generally, the stiffer the system, the larger accelerations you're going to see. And that's kind of I'm starting to get off track here, but when we're talking about base isolation, in my opinion, if you're going to earthquake-proof a building, base isolation is probably the only way to do it. But the whole, the basis behind base isolation is you're elongating the period of your structure. You're making it more flexible such that it reduces, it attracts less load, faking out your earthquake. To what extent the structural redundancy may help to recenter a building by itself? As we saw in the last results, if the PT elements yielded, your structure degrades very rapidly, meaning that you're not going to recover any elastic rebound. And so, yeah, from a redundancy point of view, I don't know how you can be redundant in your PT elements. So that is something of, I guess, that you have to be very, very mindful of when you're designing self-centering systems, is what happens if your PT yields. If it's a rocking wall system, if your PT yields, you might be able to recenter naturally through gravity. But if it's a beam to column rocking joint and your PT yields, you probably might be out of luck. So I don't know if that answered the question, but yeah. So the recentering is all affected by the PT, by whatever PT elements that you put in.
You have another question where the building is divided into 3 sections separately by flexible structure members. How does this affect the vibration of the building?
Okay, so when the building is divided into 3 sections separated by flexible structural members, I'm assuming that you're putting a seismic joint somewhere. And if you put a seismic joint in the building, then you literally have 3 different buildings, and you have to put a lateral system in each section of the building. So I don't know if that answers the question, but yeah, so divided into 3 sections. So yeah, I'm assuming that you're talking about seismic joints.
You can also unmute yourself and ask you the question directly yourself.
Someone raised their hand. Yeah.
So, using matching target spectrum by selecting ground motion according to code gives sometimes varying values. Why?
Well, ground motions are just, I mean, they're all random, right? And so the ground motions that we select, especially if we're taking historical records, we're taking them from all over the world. And each ground motion is going to have its own unique characteristics depending on the soil profiles it was taken from, where it was, and hopefully you never want to use an acceleration record that was recorded on a building. But I'm not a seismologist, so I probably can't appropriately or technically answer this question the way you would probably like. But yeah, there is not one ground motion that that we can use to design any one structure, and you know, we basically have to take a probabilistic approach and use a suite of ground motions, because one ground motion isn't going to cover is not going to give you the reliable response that you get on a building structure. So you have to use a suite. I don't know if that answered your question. If not, please type in but I guess the one thing I do want to say, though, I guess I didn't answer the part about the matching the target spectrum, was that so we take a ground motion, we scale them, and we scale them to a target spectrum based on anchoring the spectra of the ground motions to an anchoring period. So if we have a structure that has, so each structure of course has its own unique fundamental periods, and in order to make sure that we can induce damage to that building for the given run, we scale our ground motions such that they are spectrally anchored to that fundamental period. That's kind of the basis of why we scale ground motions and not just use them randomly.
I think those are the questions, and I don't want to extend this too much. So again, I would like to thank Dr. Dowden and also the audience, to the folks who logged in online. So we will be sending a short survey tomorrow, and we would appreciate your feedback. Also, if you have an interesting topic in your mind, you'd like us to find a speaker for that topic, or if you're willing to present yourself, your research, you're more than welcome to do so. Our email address is sei@mtu.edu. That's our email address. And also, I will be sending a Google form right now so that you can just fill that Google form, and we will be in touch. So thank you again, Dr. Dowden.
Thank you for having me, and thank you for everybody for listening in. Thanks for coming.